Good morning everyone. So today's session we will be continuing about the previous session, that is about the introduction to compressible flows. So last class what we have studied about what is compressible flow, which we have seen. So compressible flow is nothing but, so it is a density variable. So where there is when a flow field is at a higher velocity at that particular time, there is a change in pressure. Due to the change in pressure, there is a change in the density is also there. So due to which we are telling that compressible flow means the density variable is there. So when it comes to in contrast with the incompressible flow, so what we are telling about the incompressible flow means, so where the velocity of the flow is very less. So due to which the pressure changes which are going to be there is also less. So when compared to the pressure changes, the density changes are very less. So which means that it is negligible, or we can consider it as a constant. So that's why we are telling incompressible flow means the density is constant, whereas compressible flow means as it having the higher velocity, so there is a larger change in the pressure. So with that there is a change in the density. So with this one what we have seen about the formula is that one dp equal to d rho equal to tau into dp, right? So which means that change in pressure is directly proportional to the change in the density. So where there is a change is there significant amount, so correspondingly there is a change in the density also will be occurring. So due to, and not only this one, depending on the effect of the compressibility. So what we have seen, the compressibility is nothing but minus 1 by v dv by dp, right? So this is the compressibility. So when there is a change, so in the compressibility effect, so then we will be having the, so what is the formula? So d rho equal to p rho into tau into d, right? So that change in the pressure, so we will be having the change in the density will be there. So that's what the gas flow. Suppose if you are considering gas velocity is less than Mach 0.3, so the associated pressure changes will be small. So even though we will be having the larger tau value for the gases, but from the equation what we can tell, del rho will be very small. So that is why when dp will be of less value, so then d rho will also correspondingly less value will be there. So these two are corresponding to the less value. So due to which we are considering, assuming it that particular gas field as an incompressible flow. So if we are considering an example, flight velocity of airplanes from the time of Wright brothers, so considering from the 1903 to the 1939, the speed is varying. So from one to the another one, so which is less than the Mach 0.0. So which means that whatever we are considering, it is considering for the flow field, for the incompressible flow. So with flow velocities higher than the 0.3, that is 0.3 speed of sound, associated with what we are telling. So when this higher the velocities mean, the pressure changes will be more. So correspondingly, there is a larger changes in the density will be there. So it means the higher at the time of the higher velocity, there is a change in the pressure, correspondingly larger density changes will be there. So that particular one we are calling it as a compressible flow. So at that time what we will be seeing, the compressibility effects on the airplane aerodynamics is important from that time. So of the advanced high performance aircraft from the 1940s, we are seeing the compressibility effects also, considering it as one of the important factor. So indeed modern high speed and subsonic supersonic aircraft today, the older incompressible theories are wholly inadequate, and compressible flows analysis is must be needed. So compressible flow is considered as one where there is a change in the pressure that be over the characteristic length of the flow multiplied by the compressibility results in the fractional change in the density, that is dou rho by dou no is too large means to be ignored. So it means we can't ignore the density changes. So it means we have to consider those density changes also into the picture. It means the flow which we are considering it to the compressible flow. So in this particular one, what we are telling, so most of the practical problems, if d changes is of 5% is there, density changing is of 5% is there, or more than that, is there, means we are considering that flow to be a compressible flow. So that is one of the factor which we are telling why the importance of the density is there. So if your density is small or lesser, you can consider it as a constant. So at that time, we will be calling it as a flow is incompressible flow. Flow is considered as an incompressible flow. So as the flow is increasing, what will be happening? As the velocity of the flow is increasing, so there is a change in the pressure changes will be there. So P change will be there. So that is pressure changes will be there. So correspondingly the density changes will be there. So at those density changes at the higher velocities will be, we won't be able to neglect it. So that's why we will have to consider the effect of the compressibility inside the flow. So for that, what we have to see is like, as we are telling, the density changes are above 5% or more means the flow is compressible. So before that, what we are stating that flow velocities are more increasing. That means what it means is like, as the flow velocity is increasing, there is a change in the density. So it means that the characteristics of flow regime is also will vary with respect to the flow velocity. So for that particular one, we talk about now what are the flow regimes, different categories of it. So before going to that one, what we will be considering it is like, we will be considering the far free stream of the body. The flow is uniform. So on the far free stream of the body, the flow we are telling it uniform flow is there. So with the free stream velocity, we are telling uniform flow is there. There is no change in the flow direction. So V infinity, that is free stream we are considering. So after that one, we are seeing, let's see about the what is a streamline. So streamline is nothing but it is a curve in the flow field whose tangent is which is a tangent to the local velocity vector V at every point along the curve. So that particular one we will be calling it as a streamline. So now what we will be seeing, we will be considering a flow field. So suppose this is a flow field if you are considering. So inside this particular flow field, at any point, arbitrary point you consider. So at that arbitrary point, what will be there? Generally flow properties means what we consider pressure, temperature, density, and what the velocity will be there. So these all will be the local pressure, temperature, density, and velocity at that particular point. So all these points, all these quantities, what will be there are the point properties. So at this particular point, we might be having, suppose consider it as P1, T1, ρ1, V1. So if we are considering it another point, so that particular point, this is particular point 1 if you are considering, at point if you are considering means the pressure, temperature, density and velocity might be where. So these quantities from one point to the another point, there might be the variation will be there. Okay. Suppose if speed of sound, so is a uniform free stream. So then the ratio of velocity of the object divided by the speed of sound is nothing but Mach number. So this is the number which will be telling us the flow response. So now this is nothing but what? So we know what is the speed of sound is nothing but under root of gamma RT, right? So V is the velocity of the object. Now what we are telling compressible flow means as the flow velocity is increased, higher the flow, right? Means basically we can tell Mach number 0.3, we will be calling it as a compressible flow. Mach number less than 0.3, we will be calling it as an incompressible flow. Basically less than this one, the density is constant. So above this one, density varies. So for that, considering this as the base one, above 0.3 Mach number, we are considering it as a compressible flow. So at that time, what will be here, we can tell if the more we already know this, the constant value of 340 meter per second, and we will be having the velocity. If the change is there means, then we will be having the Mach number variations will be coming. So coming, we'll see that how the categories of external flow for external environment. So as I told, if Mach number is less than 0.3, we will be considering it as a incompressible flow. Whatever the density change is there, I am not telling the density change will not be there. So the density changes will be nevertheless. So those are the negligible, or we can consider it as a constant. So the Mach number between the 0.3 to 0.8, we will be calling it as a subsonic flow, where density changes are significant and the shock waves will not be appear. It means the flow will not be, the formation of shock waves means there won't be abrupt changes in the flow field will not be there. So that's why the shock wave formation will not be happening at this particular range of the Mach number. Okay, so next coming to the Mach number between the 0.8 to 1.2, the flow is calling it as a transonic flow. Okay, so here the shock wave will be appear and divide the subsonic and supersonic flow regime. So there is a separation of the subsonic and supersonic flow regime will be there. And there is one more call. So if m equal to Mach number equal to 1, that we will be calling it as a sonic flow means. Okay, so at that time what we will be calling it? Velocity of the object will be equal to speed of sound, right? So when these two are equal, then only we will be having the Mach number, right? 1, right? So at this time we will be calling the flow is as a sonic flow, we will be calling it. So next coming to the transonic flow will be how it is categorized by the mixed region of locally subsonic and supersonic. Okay, so actually basically what we will be calling subsonic flow is Mach number less than 1. Okay, so this one we will be calling it as a subsonic flow. So Mach number above 1 we will be calling it as a supersonic flow. So but between the transition of subsonic to supersonic, there is a range of 0.8 to 1.2 that we will be calling it as a transonic flow. That's why here they have said that transonic flow is categorized by a mixed region of locally subsonic and supersonic flows. So next coming if 1.5 to 5, so that we will be calling it as a less than 5, that we will be calling it as a supersonic flow. Here flow field everywhere will be the above acoustic sound only will be there. Shock wave will be appears across the shock wave and streamline changes the direction continuously. There is a streamline changing will be there continuously. So here you can see that next is Mach number above 5, right? So if you are having above 5 Mach number, what we will be having? We will be calling it as a hypersonic flow, where the temperature, density and pressure will be increases almost explosively across the shock wave. There is a changes in the temperature, pressure, density will be there. So that we will be calling it as a hypersonic flow. So here you can see that entire based along with the Mach number, the flow regime is, as I told, from Mach number from 0 to 0.3, we will be calling it as incompressible flow, where density is negligible, or we can consider it as a constant. The changes will not be considering into the picture. So when it comes to the 0.3 to 1, we will be taking it as a 0.8 till that one is the subsonic region, until 1 we will be calling it generally. So then 0.8 to 0.2 we will be calling it as a transonic flow, and between the 5 we will be having the less than the 5 will be having the supersonic flow. Above supersonic flow will be of the hypersonic flow. More than that one, hypervelocity flow we will be calling. So this is the regime of the flow regime of compressible flows based on Mach number. Okay. So now in detail we will be studying about these flow regimes. So what we are telling, subsonic flow is nothing but local Mach number is less than unit. So that is less than 1. So such a flow where m is less than 1 at every point, as you can see here, right? So from this one, what we are understanding, this is nothing but the flow field. So this is a flow field over an airfoil. So inside that particular flow field, what we are giving a Mach number of less than 0.8 we are taking it. So here what you can see, entire flow field we are having the Mach number is less than 1 only. So where everywhere, every point, hence the flow velocity is less than the speed of flow. The flow field is characterized by smooth streamlines and continuously varying properties. As I told, from one point to another point, there will be same properties will not be there. Though the flow is smooth is there is a change in the properties will be happening from one location to the another location. So initially we are having the straight and parallel streamlines is there in the free stream. So that will be begin to deflect from the free stream of the body, and from there it will be there according to the position, how the shape of the body is. As the flow passes over the airfoil, the V at the top surface increases above the free stream value. So velocity, what will be there at the Mach number? Now what we are telling here, the free stream is passing at the less than Mach 8. So here less than 0.8 we are telling. So as it passing over the airfoil, the M and means correspondingly, V is increases means corresponding M will also increase. So this is increasing and M also increasing. But overall, what is the value of Mach number will be of the less than 1 only. It will not be crossing the more than 1. So that is the one thing which we have to consider inside a subsonic flow. Means inside a subsonic flow, we will be having the Mach number is less than 1 throughout the flow field. Right. So now, next coming to the transonic flow. So what we are telling, if Mach number remains subsonic, but it is sufficiently near to 0.1. So what is it? So 0. What we are telling, generally subsonic flow is less than 1 we are stating it, right? So that's why here if infinity remains subsonic, it is sufficiently near to the 1, what will be happening? The flow expansion over the top surface of the airfoil may vary to the local supersonic region. So you can see here, so in this region what it is there, here at the front we are having the less than Mach 1, but in this particular one, the reason Mach is greater than 1. After the certain region, we are having the less than 1. So here, there is a formation of the shock wave we will be seeing. So it means result in the local supersonic regions we will be observing. So such a mixed region of the flow is defined as a transonic flow, where we can see we are having a subsonic region, we are having again supersonic region, again we are having the subsonic region. So this mixed region of the flow is defined as a transonic flow. So if M is 1 but not enough to produce a pocket of locally supersonic flow. So this pocket will be terminating with a shock wave across which there will be discontinuous, sometimes rather than changes in the flow properties. So whatever the pocket which is forming at this particular location across the shock wave, it will be discontinuous. Sometimes what it will be there due to this one. So as you know, if you are increasing the flow velocity means what we are stating that there is a change in pressure and correspondingly there is a change in the density, right? It means the flow properties will be varying inside this particular pocket. So now further Mach number is increased. So what is that now locally we have seen previously from 0.8 to Mach number less than 1, that is of subsonic region time, how the mixture of the Mach number like flow which we have seen, right? Now if Mach number is further increased between 1 to 1 point above unity, the shock pattern will move the leading edge of the airfoil and second wave appears upstream of the leading edge. Here you can see the formation of a bow shock wave ahead we will be seeing. So this second shock is nothing but bow shock wave we will be calling ahead of the shock. So here you can see as the flow stream is passing, the above unit 1 is their Mach number. So ahead of this one, when the flow is passing, there is a 1 at a certain distance. So at certain distance, that is upstream, we will be having a Mach number which is of less than. After certain, there is an increasing in the Mach number is there. And this ahead which is forming, we will be calling it as a bow shock wave. So in front of the bow shock, the streamlines are straight and parallel with the uniform supersonic free stream Mach number. So whatever the flow is there, that is of same. So in passing through the part of the bow, which is nearly normal to the free stream, so the flow becomes subsonic. So since it is of the same, bow shock nearly normal to the free stream is there. That is the reason we are having at this location we are having the flow as a subsonic. So you can see the flow is like normal only, right? So that's why we are having at this particular region we are having a subsonic region we will be calling. So next, supersonic flow. So what is supersonic flow as we told earlier? So basically it is like above 1 we will be calling it. But since we are taking the transonic flow also will be there between these two regions, between 0.8 to 1.2. So more than above everywhere we will be calling it as supersonic, and specifically we will be mentioning the above 1 point if you are taking. So now what we will take? So consider a wedge. So this is a flow or a wedge we will be considering. So a straight oblique shock wave is attached to the, actually normal shock means it will be the perpendicular one. So oblique shock means it is at a certain angle. So we will see this in detail about this in the module 2. So but for time being you understand that oblique shock means at a certain angle which is the wave attached to sharp nose of the edge. So across this shock wave the streamlines are changing the continuously. There is a change in the streamline is there. Now ahead of the shock the streamlines are straight, parallel and horizontal. Behind the shock wave also they remain the straight and all, but what it will be taking? It will be taking the shape of the wedge. Now suppose if I am telling like previously here, this is the flow region is there. Now what I am telling at this particular, this is the wedge we are considering. So for this wedge there is a shock wave formation we are stating that it will be forming, that is oblique shock wave. So after the crossing of the shock wave, what it is doing is like the flow field is considering the shape of that, taking the direction of the wedge surface whatever is there. So the flow is subsonic at the upstream and the downstream of the oblique shock wave. So you can see here we are telling Mach is above 1.2. Here also we are stating the Mach number is above 1. That is nothing but the supersonic region only there. So here the temperature, pressure, density of the flow is increased almost entire the shock. Means ahead and the behind the shock wave there is a changes in the flow properties we can state. Right. So next is Mach number above 5. So that we will be calling it as a hypersonic flow, right? So there is a higher speed means there is an increase in the flow properties changes also. Here also it will be more, it will be there. So at the same time what we will be having? Shock wave. Previously what it is there for the wedge, we are having a shock wave formation is there, but you can see clearly the formation of the shock wave at a, it's not towards the surface, right? At a certain distance it is there, at a certain angle we can tell. So but when it has it, if you are seeing the same thing, what is happening here, the oblique shock wave whatever it is forming, it is coming closer to the surface of the body. The flow field between the shock wave, the body becomes more hot indeed, enough to dissociate even the ionize the gases. So at this particular flow regime, what is happening, like ionization of the gases can also happening. If the flow will become more hot, the temperature will be of more, it will be there at this particular flow regime. So these affect thin shock layers and hot chemically reacting gases at the complex analysis of this such kind of the flows. At this regime, studying about the flows is very difficult, as we are stating that the flow between the shock and the body becomes very hot, because as higher the velocity is going on at that particular height, there is a changing in the temperature will be occurring at that atmosphere basically. So that much hot which is enough to dissociate or even ionize the gas particles. So that is the one thing where to study about those thin shock layers and the how the interaction effect of those heatness which is occurring on the body will become complexity to analyze such kind of flows in the compressible flows. So you can tell above Mach 5 we are calling it as a hypersonic flow. So Mach 5 will be dividing us between the supersonic and hypersonic flow. So in reality what we will be there is like the special characteristic associated with the hypersonic flow, as Mach number is increased, that basically depending on the shape of the body and the free stream density value is there. The Mach number in which the important depending on greatly on the how the shape of the body is there and the free stream density value at that time, at that particular location what it will be there. So basically majorly it will be depending on the those two characters, that is one is the shape of the body and the free stream density. So this is about the hypersonic flow. So now coming to the Mach number, as I stated earlier, it is nothing but the speed of the object to the speed of the sound, that is Mach number we are stating. So here you can see different, based on the Mach number, the different flights are there. So Mach number subsonic less than 1, subsonic transonic region, we can tell like transport flights will be there. In the higher we will be having the fighter, and the more the larger we will be taking in space shuttles or the re-entry vehicles, all those will be falls under the above Mach number 5. So we will see in detail what kind of flights will be there. So less than Mach number 1 we will be having the general aviation will be there. So where we will be having the propulsion with propeller propulsion will be there. Aluminium skin we will be taking, and the straightening which we can it can vary also. Now as the technology has been increased, as the aviation industry has been evolved, so we are changing it to the different kind of the wing cross section. So what we are doing here is like at this particular time, we are neglecting the compressibility effect. That means we are considering the density is nearly to the constant, or we are not taking the density into a picture. Like we are neglecting the density effect at this. So next is the high subsonic region. That is in the sonic we can tell like Mach number where it is nearly equal to the 1. So we will be calling it airlines where we will be having the turbofan engine. So here also skin we will be of the aluminum, and we will be using the swept wing here. So as if you remember in a transonic flow, so where we are having the Mach number, we have less than 0.8 we are having at this particular region. As the flow is passing on, there is a formation of Mach number above 1 is there, that supersonic region is there. To avoid this particular one, what we will be using is like the concept of the swept wings has been taken into the picture. Okay. So here compressibility effects and the air density may vary because of local shock wave expansion or the flow choking is happening at this particular region. So now lower supersonic region, that is Mach number less than 3. So here fighter planes we can consider. So afterburner engines will be used here. So aluminum skin itself they will be using, and here also swept wings will be considered. So here also same compressibility effects will be considered, and the density will be varies because of the formation of the shock waves, expansion of the flow choking occurring at this particular region. So at the hypersonic, so we will be having the spy planes, ramjet engines we will be having, and the skin will be the titanium and the small wings. So why it is of the skin will be varying is because of the effect of the higher the flow moves, there is a what we stated earlier is that there is a changing in the flow properties, right? So due to which we are seeing the material where it will be able to withstand those abrupt changes in the temperature also. So in the supersonic effect, same we will be considering the compressibility effect. Local density varies because of the shock waves and the expansion waves formed. So next, low hypersonic region explains it is basically made up of the scramjet and ramjet rocket engines, and cool titanium or the nickel skin will be using, and here we will be having the shorter wing sections only. We don't have the larger sections like in commercial aircrafts. So large variation in air density will be there. Pressure occurs will be also there because of the shock waves and expansion. Right? Now next one is the hypersonic re-entry or the hypervelocity, which we are telling which we are doing. So those are basically nothing but the space shuttles. So we will be having the rocket engines. We will be using the thermal protection system because it has to go at higher atmosphere where there is changes in the weather conditions. As the height is increases, we are having the flow property changes are there. So in order to sustain that one, we will be using the thermal protection, and we will be having this short blunt wings will be there. So the air density is very low because of the re-entry occurs at many miles from the above Earth surface. The strong shock waves will be generated on the lower surface of the spacecraft. So this is the hypersonic re-entry vehicle system which is there. So now this is overall, if you see the relation with the Mach number and the flow regime, whether the density variation will be there or not, or whether the shock wave formation. So if it is less than 0.3, what we are telling, the flow is incompressible, density is negligible or constant, and shock wave formation will not be happening. So less than 0.8, we are having the subsonic, density changes will be occur, gradient change, and shock wave formation will be not happen. But between 0.8 to 0.2 transonic region, there is a significant change in the density gradient, and first appearance of the shock waves will be seen here. So at 0.1 to 0.3 supersonic regime, we will be calling it flow regime. Density effect will be there. And there is a formation of the shock waves. So like shock wave formation we can see directly here. So if you are having the Mach number is above hypersonic flow, the density gradient dominant will be dominant position will be there, and shock wave also will be in the dominant shock waves we can see at this particular flow regime. So these all are about the flow regimes. So what it is like, density is constant or negligible means incompressible flow. So if density changes, compressible flow. So inside this one, these are the different flow regimes which we have seen, right? So now we'll talk about what is a continuum. So consider the gas to be a continuum. So clearly a gas is composed of large number of discrete atoms or molecules. All will be moving in the random fashion and colliding with each other. So that's nothing but the gas to be in a continuum. So it means that gas will be a large number of molecules or atoms will be there. So they will be moving randomly here and there. If you are taking the molecules, they will be continuously moving here and there and they will be colliding with each other as well. So this macroscopic picture of the gas is essential to understand what are the thermodynamic and chemical properties of high temperature gas. When these molecules are colliding with each other, but considering that particular gas, we will be able to understand what is the thermodynamic and chemical properties behavior at high temperature time. However, in deriving this fundamental equation and concepts of the fluid flow, we take the advantage of the fact that gas usually contains a large number of molecules. Hence, microscopic basis, whatever the fluid it will be there, it is a continuous material we will be considering. This continuous assumption is violated only when the distance between the atoms or molecules between the collision is large, that is same order of magnitude or the characteristics of dimension of the flow. This implies that low density or the rare flow. So what we are telling, it will be violated when the distance between the two atoms or between the two molecules collision is large. At that particular time, we will be calling it as a low density or the rare flow. The extreme situation where the mean free path is much larger than the characteristic length, where virtually no molecular collision take place, that is like free molecular flow. It means like here, somewhere randomly, here, at this point it is there, means those mean free path between the two molecules, if it is large, means that we will be calling it as a free molecular flow. So in this case, the flow is essentially is upstream and remotely spaced particles. So low density and free molecular process rather special cases in the whole spectrum of fluid mechanics occurring in the flight only at higher altitudes will be there. So in those cases only we will be seeing this one. Otherwise, rather than that, will be most of the time we will be considering about the continuum. So apart from these continuum topic, so we will be categorizing the flow fields also differently. So that is of the basically viscous flows and non-viscous flows. Okay, so what I mean by the viscous flow is nothing but there is a change in the viscosity, thermal conduction and the dissipation. So these two are the changes are there in a flow, means then viscous flow will be there. So when it comes to the non-viscous flows, means viscosity will be constant and there won't be much change will be the thermal conduction which will be there. So this is the overall about the topic of what we have seen yesterday, covered with the compressible flow introduction. So we have seen the isothermal compressibility, then we have seen isentropic, then what we have seen? Then we have seen the Mach number relation, how it will be like changes for compressible flow and incompressible flow we have seen. Then today class we have seen about the flow regimes, we have seen what are the different types of flow regimes, how they have been categorized we have seen, and we have talked about the continuum and we have seen about the variation, like we have talked about the what is the viscous flow and non-viscous flow. So for tomorrow's session, as here we stated that measure of the effect of the thermodynamic properties we have to know. So we will see basic review on thermodynamics and fluid mechanics in the next session, so that we will understand initially all the concept we will revise and we will be going towards directly to the how the governing equation has been formed for the compressible flows. Okay, so this is the textbook which has been referred for this particular session, that is Modern Compressible Flow with Historical Perspective by Cherry Anderson, and you can refer the Fundamentals of Aerodynamics textbook as well. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.